All right, so today's video is about an important topic if you're running software, particularly Python code, on a computer with a lot of resources, say hundreds of processors, multiple GPUs. The trick when writing parallel software to use that entire system is that you have to tell each piece of Python code that's running which resources it's allowed to use, because if they're all the same, each individual Python is going to compete with all of the others. Now to illustrate this, we'll show a simple example which can run effectively on a single computer. So here I've got an example that's doing some matrix math, and you're going to see it takes about 20 seconds to run on a single or with only one Python worker, and you can see that on the right here. And you can see that it's using about 9 CPUs. I have 12 on this computer. So it's doing a good job of using everything. Now, it takes about 19 seconds. Now, if I make it such that it runs 6 copies, this should, in theory, be no slower. It's not running a bigger problem. It's not accessing more resources. So it should take about the same amount of time, in theory. Now, in practice, that's not what happens. You're going to see here in a couple seconds that it takes slightly longer, 21 seconds. Now, what's happening here is that each of the Python programs doesn't know that the other ones exist, and they're competing with each other for resources. So what you need to do in problems like this, where you're running parallel multiple copies of Python that are each using very expensive codes, that they need to know what resources they're allowed to use, such as which CPUs, or in a multi-GPU system, which GPUs. And that will ensure that they don't compete with each other, that they properly spread out across the system. You can see here, each rank is assigned its own copy of CPU cores, and voila, it takes about the same amount of time as if we used one core. No competition, or one worker rather, no competition. So the way that this happens under the hood, and the reason why it's important, is that we're running an example problem that uses PyTorch. So we'll go up here at the top first. You'll see that I've got a PyTorch function here that creates a big matrix of 9 million entries. It does a matrix multiplication, it does some division, and it repeats for a couple times. So this is very numerically intensive, and well, not very, but it's notably intensive, enough to the point that it can use multiple CPU threads, which is what you saw happening earlier, where there was more than one thread happening. Now, the way that that works in PyTorch is it uses a code called OpenMP in order to do the spreading across multiple cores on a CPU. And we can show you what that OpenMP is doing by changing an environment variable. So we're going to tell it to display Affinity. And we'll put that in all caps just to make sure it works. And you can see, voila. Each of these different Python workers is printing out that it has been assigned to have affinity towards different CPU cores on the system. Number one got, or the first one to print got 12 through 15, and there we go. This runs properly. Now, if I turn it back off, let's show you what's happening. Each core is acting as if it's allowed to use all 24 threads across 12 processor cores on my system, and that's what's causing the interference with each other. And you can actually see the interference with this load average here. If the load average goes above the number of processors you have, which doesn't appear like it's going to happen in this run, but when that happens, it's an indication that there's some resource binding or some resource competition happening. So that's what we're doing here. I've assigned it such that each of my processors, or sorry, each of my Python processes rather, sees different processors. And that lets the program run faster because they're not competing. So that's the overall concept. Make sure each process uses different processors, CPU, or graphics. The way that we make that happen in Python looks a little bit like this. So let's open up the source code and walk through there. So resource pinning. So the way that we pin processes in Python to specific cores is using a function called schedule set affinity. What that is doing is it's telling the operating system that this process, 0 refers to itself, is only allowed to use a certain list of cores. So what happens then, the processor is limited to a certain number of cores. When OpenMP goes to run a matrix multiplication in multiple cores, it will look to that table. It'll find that it's a reduced set, not all 24, and act accordingly. You saw that in those affinity printouts. So that's the way that we achieve this. There are a few other ways to make that happen. There's also setting environment variables. If I do os.environ omp, I think I can set the thread affinity this way. I didn't actually look this up before recording the tutorial, so definitely check that one. You could do something like this to specify more directly. But the reason why I don't do this, or didn't do it in my particular example, was because this particular example here, where I'm telling OpenMP not to, or to only use a certain cores, only works if that process uses OpenMP. If there's another parallel library behind it, the environment variable that I'm showing you in this line won't do anything. So that's why I'm using the very specific operation, schedule set affinity, in order to make this happen. So that's the function. That's how I make it work. Now, what needs to happen in order for this to function is that I need to run this little function here at the beginning of a Python worker starting. The way you do that in Python is to pass this function and these arguments, the rank queue and total ranks, to the Python parallel executor when you start it. So that's what is happening here. I'm starting a Python, or a pool of Python workers that are going to do my tasks. I'm telling it how many. I'm telling it here that it's going to launch them as spawned processes, not forked. We're not going to go down that route today, but that's what this is. And then I'm passing it my keyword arguments that says, oh, the initializer function that I call is pinned to resource, and pass that a queue with and the number of workers as its input arguments. So that means when this starts up here, the first thing that happens is that it loads the function pinned to resources, which gets called. The first thing that function does is it pops the rank off of the queue. I determine which cores I'm allowed to have. I assign them, and I'm done. This function has executed, at which point that worker will actually execute my little Python PyTorch function here. So to recap, the way that we make thread affinity happen in Python is that when you create your process, your pool of workers, you tell them an initialization function that it can use to look up what worker number it is. I do that via a queue of numbers. The first one gets 0, the second one gets 1, and so on, which sets affinity using the OS set affinity function, which is one of many ways to do it. It happens to be the most general one. It also is the one that works only on Linux. So if you're running a Windows computer, I believe you'll have to go to use that set affinity button, but generally if you're running a multi-GPU workstation, it's probably running Linux anyway. So I didn't even test how to do that for the purposes of this tutorial on Windows. So that's the basics of it. Now, the one thing that's a quick note here, if you're doing GPU affinity as well, which I only have one GPU on this system, so the demo would not have worked pretty well, you can do that using environment variables. So here I'm setting an environment variable via Python. It's environ. CUDA visible devices equals string rank. So what that's going to do is tell that this particular worker that it's assigned to GPU number, in this case rank. Now, how that works with CUDA is that when CUDA starts up and prepares to run calculations on your graphics processor, it's going to look at this environment variable, determine which processor it's allowed to use, and act accordingly. Very similar to how CPUs work.